Welcome to AudioCert, where the official study guides are brought to life. Today, we are undertaking a monumental deep dive. We're jumping right into the core of cloud services. Certified Cloud Security Professional, or CCSP, Domain 4 Cloud Application Security. If you think about cloud infrastructure as the engine, well, the applications running on top, they're the actual vehicle. They're what delivers the business value, right? So we're moving beyond just securing the infrastructure, the box itself. We're focusing entirely on securing the code, the access, the whole lifecycle management of those applications that handle your most sensitive data. And for many, many organizations, that's really the heart of the software as a service, or SaaS model.
Exactly. And this domain, it's really where the security professional's role shifts, I think most dramatically compared to traditional IT. See, in the old days, you controlled everything, the hardware, the OS, the application stack. But in the cloud, especially when you get into PaaS and SaaS, well, those lower layers, they're managed by the provider. So the key tension, the thing you, the learner, really need to wrap your head around is this. How do you build secure apps? How do you test them, assure them? When the underlying environment is shared, it's complex, and crucially, it's partly managed by someone else. Your application, remember, is often the primary way attackers try to get in. So understanding architecture, testing methods, identity management, all within this cloud context, it's absolutely non-negotiable.
Okay, let's start unpacking that. Domain 4.1 talks about application readiness. So before we even think about migrating an app, we have to look at the data it uses. First step, determine its sensitivity. What kind of data are we talking about? Is it personally identifiable information, PII, maybe protected health information, PHI, financial records? What is it?
Yeah, that initial decision point, classifying the data, figuring out its sensitivity, it's absolutely critical. It basically dictates the whole risk posture of migrating that application. Think about it, if the data falls under strict regulations like IPA for health info or GDPR in Europe, then the application needs really, really strong compensating controls. Sometimes those controls might even wipe out the cost savings you hope to get from the cloud. Or they might even force you to use specific regional providers who meet those stringent requirements.
Right. But, not all data is the same, is it? Sometimes the business case for moving to the cloud is just too strong to ignore, even if the data seems quite important.
Precisely. Let's say you've got a data set that changes constantly. Maybe its financial value per record is low, but it needs extreme elasticity. Imagine like a global wholesaler's product catalog. Prices, SKUs, inventory levels, or updating maybe every minute across the globe. Moving that kind of application to the cloud, it just makes sense. You maximize compute, storage efficiency. The flexibility you gain often outweighs any short-term migration costs or complexities. And, like we've touched on before, sometimes migrating actually improves your security posture. A lot of small or medium-sized businesses, frankly, they just don't have the resources for true 24/7 monitoring or the specialized security talent or the kind of geopolitical redundancy you need for really critical systems.
Like a core banking application, maybe?
Exactly, like a core banking system.
Huh.
Outsourcing the complexity of running that securely to a big, well-resourced cloud provider. That can often give you a much better, provably better security outcome than trying to struggle along keeping it in-house.
Okay, so whether it's about saving costs, gaining flexibility, or actually boosting security, the decision gets made to move. And that brings us right back to that fundamental concept, the shared responsibility model. We really need to be crystal clear on how responsibilities shift across the different service models, IaaS, PaaS, and SaaS.
Think of it like a sliding scale.
Hmm.
Figure 7.1 in the guide illustrates this really well. With infrastructure as a service, or IaaS, you, the customer, managed pretty much everything from the operating system upwards. So that includes patching the OS, managing the runtime, securing the application, securing the data, and handling governance, risk, and compliance, or GRC. The provider, they just handle the underlying physical infrastructure, the data center, the servers, the network fabric.
Okay, so you have more control, but also more responsibility in IaaS.
Right. Now move over to Platform as a Service, PaaS. Here, the provider takes on more. They manage the OS, the patching, the runtime environment like the Java virtual machine or the .NET framework. Your responsibilities then shrink, focusing mainly on the application code itself and, crucially, the data it processes and stores.
And then the furthest end of the scale is SaaS.
Software as a service. This is the most abstracted model. Here, the provider handles almost everything. The application, the platform, the infrastructure, the physical security. You, the customer, are left primarily responsible just for the integrity and classification of your data, user access management, and ensuring your use of that service meets your GRC obligations.
Okay, that model is absolutely essential for the CCSP exam. But you mentioned something earlier. There's a really important legal distinction here that can, well, trip people up. Let's say we're using PASS. The provider is responsible for patching the OS. They fail to patch a known vulnerability, and that leads to a breach of my data. Doesn't that breach fall on them? They messed up, right?
It's a great question, and the answer is tricky, contractually, financially. Yes, the provider might be liable for damages due to their negligence. You might be able to recover costs based on your service agreement. But legally, under almost all current data protection laws, globally, GDPR, ITIA, state laws, the ultimate legal responsibility for securing the data always remains with the data owner. That's you, the customer organization. So the contract might shift financial liability, but the regulatory burden, the potential fines from regulators, the mandatory breach notifications, the damage to your reputation, that liability is ultimately yours. It's not transferable in the eyes of the law.
Wow, that's a stark reality check. Really important to understand. Okay, let's pivot slightly. Let's talk about a major pitfall organizations face when they do decide to migrate. The concept of forklifting. That's covered in 4.1.2.
Forklifting, yes. It's basically the practice of taking an existing, often old, legacy enterprise application and just, well, lifting and shifting it directly into a cloud environment like a virtual private cloud or VPC without making any significant changes to the code or architecture. It's usually done for speed, expediency. But it very often leads to either catastrophic failure down the line or just creates massive technical debt.
Why is it so risky? I mean, beyond just being potentially inefficient, what are the real technical dangers?
Well, legacy applications are often built with all sorts of hidden dependencies on their original environment, things the developers might not even fully remember or document. For instance, an app might rely on some proprietary middleware that only exists on the old company servers tied to a specific license server. Or maybe it has hard-coded database connection strings pointing to an internal IP address range that simply doesn't exist in the cloud VPC.
So when it tries to make that call,
Exactly. When the application tries to execute that call to a library that isn't there or reach a network service that's vanished, it either just fails outright, maybe crashes the whole process, or sometimes worse, it just hangs indefinitely, spinning its wheels and consuming expensive cloud resources for no reason.
and the developers themselves face huge challenges in this new, unfamiliar cloud environment, right? Section 4.1.3 touches on this, things like multi-tenancy, new threats, maybe even different tools.
Oh, absolutely. The challenges are immense. Developers might discover that their favorite legacy programming language or a specific framework they relied on isn't natively supported by the cloud provider's PaaS offering. This forces them into awkward, inefficient workarounds, or maybe even a complete rewrite they didn't budget for. And then suddenly they have to get up to speed on a whole new set of cloud-specific threats, particularly those related to multi-tenancy.
Right, multi-tenancy. That core cloud concept, multiple customers sharing the same physical hardware, that introduces unique challenges we just didn't worry about as much with dedicated on-premises servers.
Yeah, the biggest challenge is the security boundary, or lack thereof in some ways. You have third-party admins. These are the cloud provider's employees. They have physical access, and sometimes logical access, to the actual servers hosting your data. But you don't employ them, you don't vet them, you don't directly control them, so your security planning must assume these admins exist. And that drives the need for controls like encrypting data at rest, so even if someone has physical access, the data itself is protected. Also, many legacy applications are just, well, badly behaved in a shared resource environment. They're often built assuming they have the full run of a dedicated server and local area network, or LAN, speeds.
They might make really inefficient database queries, for example.
Precisely. Super chatty applications, they might make dozens of small database calls back and forth just to assemble one piece of information for the user. On a dedicated server with a high-speed local network connection, fine. Maybe nobody noticed the inefficiency.
But move that chatty, inefficient design to the cloud.
And it becomes a serious problem, a resource hog. Each of those little calls consumes session resources, processor time, memory, network bandwidth, all in a shared environment. This poor design doesn't just cause performance failures or slowdowns. Crucially, in the cloud, it translates directly into higher costs for you, the customer, because you're typically billed based on resource consumption.
So job number one in securing that shared environment is paying obsessive attention to tenancy separation. We need absolute confidence in the logical isolation between different customers, preventing any kind of data bleed.
Logical isolation is really the bedrock of cloud security. We're relying heavily on the cloud provider's hypervisor technology and their configuration management to ensure that one customer's processes, memory, and data are completely separate from another's, even on the same physical machine. It's complex because, as customers, we often don't have direct visibility. We have to rely on remote administration tools provided by the vendor, and we need extensive negotiation and auditing to ensure they're using the strongest possible isolation methods and actively monitoring for things like guest-to-host escape attempts or other cross-tenant vulnerabilities.
Okay, one last point on readiness before we move to development. External communication, usually via application programming interfaces or APIs. The flexibility of using lots of different APIs is great, but it's also a huge potential risk vector, isn't it?
Huge. Absolutely huge. APIs are essentially the doors and windows into your application's functions and, more importantly, its data. So cloud customers must have a formal documented policy for vetting APIs, selecting them carefully, and deploying only validated approved APIs. You simply cannot allow developers or worst end users to just grab any convenient API off the internet and plug it into your environment without rigorous security review. This validation process has to be tightly integrated into your secure development lifecycle and your change management procedures right from the beginning. You need to trust the APIs you use.
Okay, that makes perfect sense. You have to secure the entry points. So assuming we've done our homework on readiness, data sensitivity, and the environment, we can move into the actual creation process.
Yeah.
The Secure Software Development Lifecycle, or SDLC. This is domain 4.2 and 4.3. Now, the core stages are pretty much the same as in traditional IT development, but the emphasis here is on baking security in at every single step, not just testing at the end. Let's quickly recap those 6 core stages.
Right, the 6 stages provide a framework. We have defining, designing, development, testing, secure operations, and finally disposal. And the critical point, as you said, is that if security isn't considered right from the start in defining and designing, it becomes incredibly expensive and often ineffective to try and bolt it on later during testing or operations.
Let's zoom in on those first 2 stages then. Defining, at this stage, we're not actually talking about specific technologies yet, are we?
Correct. The defining stage is purely focused on the business requirement. What problem is this application supposed to solve? Do we need a new accounting system, a customer relationship management, or CRM tool? Maybe something for inventory. It's about identifying the business need before you get locked into thinking about specific programming languages, databases, or cloud services. We want to avoid technology lock-in too early.
Got it. Business need first. Then comes designing. This is where we start drawing up the blueprints, so to speak.
Exactly. The design phase is where the architectural decisions really happen. We develop user stories, detailed descriptions of exactly what the user needs the application to do from their perspective. We start sketching out interface concepts, mock-ups, and crucially, we plan which internal systems or external third-party APIs the application will need to interact with, or perhaps which new APIs it will expose itself. Security requirements absolutely must be integrated here. Things like, this data must be encrypted at rest, or only users in the admin role can access this function. These rules get designed in, not added as an afterthought.
Makes sense. Then we hit development. That's the actual code writing.
Yeah.
And after that comes the really heavy lifting, testing.
Testing is where, as they say, the rubber meets the road. This phase typically gets broken down into 2 main streams. First, functional testing. Does the application actually do what it's supposed to do, accurately and reliably? Does it meet those business requirements from the defining phase? Second, security testing. Do all the security controls we designed in actually work? This is where we start doing things like initial penetration testing, vulnerability scanning. We'll dive deeper into those specific techniques later to actively look for weaknesses.
Okay, so once it passes testing and goes live, we enter the secure operations phase, which involves ongoing monitoring, patching, incident response. And then, eventually, every application reaches its end of life, bringing us to disposal. Why is disposal considered a distinct security concern within the lifecycle?
Disposal is critical because of the huge risk posed by running old, unsupported software. Once an application officially reaches its end of life, the vendor typically stops providing security patches for any newly discovered vulnerabilities. If you just leave that unsupported software running in your environment, well, you're essentially leaving a wide open door for attackers. It creates a massive, unnecessary attack surface that will eventually be exploited. Secure disposal means ensuring the application is properly decommissioned, the data is securely archived or destroyed according to policy, and all related accounts and access are revoked.
Right, closing the loop. And underpinning all 6 stages, you need robust quality assurance, or QA processes, that's covered in 4.3.3.
Yes, QA isn't really a separate stage, but rather a continuous, systematic process of managing and inspecting the entire SDLC. The goal of QA is to minimize the introduction of errors, both functional bugs and security flaws throughout the process. It's about ensuring the final product consistently meets all the specified functional and security requirements, trying to catch human errors early.
Now, linking this structured SDLC process back to day-to-day operational reality requires really strict configuration management, or CM, and versioning. That's 4.3.5. And I imagine this gets particularly tricky if development teams are using Agile or DevOps methods that prioritize speed over meticulous documentation.
Oh, it's a huge challenge. CM practices have to synchronize perfectly with the SDLC, whatever methodology you're using. As soon as a design is approved, maybe even earlier, the project, including all its code components, needs to be formally entered into the CM system. You need robust version control like Git or SVN and clear documentation tracking every single change. Think about it. If a critical security vulnerability is found and fixed in, say, version 3.1 of a component, but that fix isn't properly documented and tracked through the CM system, well, a developer working on version 4.0 might completely unknowingly reintroduce that exact same flaw because they branched off an earlier unfixed version or missed the update. Speed, especially in pure Agile environments, can sometimes come at the direct expense of that meticulous tracking and documentation, which is a significant security risk.
So we need a way to formalize and track the security requirements across the organization and within specific applications. This brings us to an important standard. ISO IEC 27034-. It introduces 2 key framework concepts, the ONF and the ANF.
Right. These are important for structuring how you manage application security controls. First, you have the Organizational Normative Framework, or ONF. Think of the ONF as the master library or catalog. It's the comprehensive documented list of all the approved application security controls, secure coding best practices, required processes, and security guidelines that are used across the entire organization. It's the top-level source of truth for application security.
Okay, the master list. So what's the Application Normative Framework, the ANF?
The ANF is a specific, tailored subset of the ONF. For any single application you're building or managing, its ANF defines precisely which controls from the master ONF are required for that specific application based on its risk profile, data sensitivity, and functionality. So if application Z handles highly sensitive financial data, its ANF is going to be pretty extensive. It'll likely mandate things like strong multi-factor authentication, data encryption, detailed audit logging, etc. But if application Y is just a simple, low-risk internal tool for booking meeting rooms, its ANF will be much smaller, maybe just requiring basic authentication and input validation.
Could you maybe walk us through the relationship between them again, just to make sure we've got that distinction clear, like a simple example?
Sure. Let's say your organization's ONF, the master list, contains 50 possible security controls in total. Everything from password complexity rules to secure session management to specific encryption algorithms. Now you're building application A, a public-facing e-commerce site. Based on its risk, its ANF might specify that it needs to implement controls #1 input validation, #5 strong authentication, and #10 TLS encryption from the ONF. Then you build application B, an internal HR portal. Its ANF might only require controls #2 role-based access control, and #5 strong authentication. It doesn't need #1 or #10 from the ONF because its risk profile is different. So the relationship from the ONF to the ANFs is one to many. One master framework, ONF, can inform many specific application frameworks, ANFs. But crucially, the relationship the other way, from an ANF back to the ONF, must be one-to-one. Every single control listed in an application's specific ANF must map directly back to a defined approved control within the master ONF. This ensures that individual project teams aren't just making up their own security rules or implementing controls that haven't been vetted and approved by the organization's overall security strategy. It provides consistency and traceability.
Got it. ONF is the big library. ANF is the specific reading list for one project, drawn only from that library. Okay. Now, if applications are the heart of the service, then identity and access management, IAM, is surely the gatekeeper protecting that heart. This is domain 4.7. IAM covers the people, the processes, the technology, everything involved in managing who users are and what they're allowed to do in the cloud environment. And the functionality here is often split into 2 main areas, right?
That's right. There's a clear functional split. First, you have identity management. This part is all about establishing who someone is. It includes provisioning new user accounts, issuing unique identity assertions, like user ID and password, and managing those credentials over their lifecycle. password resets, changes, deactivation. It answers the question, who are you?
Okay, so identity management establishes who you are. Then access management comes into play.
Which exactly. Once your identity is established and verified, access management takes over to control what you are allowed to do. It has three core functions baked into it. First is authentication. This is the process of actually verifying the identity assertion you presented. Did the password match the user ID? Is the biometric scan valid? Second is authorization. Okay, we've verified who you are. Now what are you permitted to access? This often involves checking the verified identity against rules, like an access control list, ACL, or role-based permissions, to determine can this user read this file, or can they execute this function? And the third piece is policy management. This covers the underlying mechanisms and rules used to enforce those authorization decisions based on the organization's security policies and business needs.
And all this identity information, the user IDs, the attributes, the credentials, it has to live somewhere. That brings us to identity repositories and directory services covered in 4.7.2.
Right. These repositories are the authoritative source, the storehouse, for all the attributes associated with every identity in the system. Things like usernames, passwords, or hashes of passwords, security group memberships, roles, contact information, access entitlements. It's all in there. Directory services are the technologies used to manage and query these repositories. Common examples include LDAV, Lightweight Directory Access Protocol, the older X1500 standard, Microsoft's Active Directory, which is built on LDP, and things like Novell eDirectory. And it should go without saying, this repository, this directory service, it is arguably the single most sensitive component in the entire enterprise IT environment. A breach here is absolutely catastrophic. If an attacker compromises the directory, they essentially get the keys to the kingdom. They can see the entire user structure, potentially steal credentials, and impersonate almost anyone. Protecting the directory is paramount.
Okay, super critical component. Now, to make life easier for users who need to access lots of different applications, we often implement single sign-on, or SSO, that's 4.7.3. The idea is you log in once, and then you can access multiple different systems or resources without having to log in again each time.
Yeah, the user convenience benefit of SSO is undeniable. Log in once to a central authentication server, and then accessing other connected applications happens transparently in the background. But, and it's a big but, the risk profile increases dramatically with SSO. First, implementing SSO correctly, especially across diverse applications, can be surprisingly complex and prone to misconfiguration. More importantly, though, SSO creates a massive single point of failure. If that central authentication server goes down, potentially nobody can log into any of the connected applications. And from a security perspective, it creates a much larger attack surface concentrated on that one credential. If an attacker manages to steal that single SSO credential,
They get access to everything linked to it.
exactly, they hit the jackpot. Instead of needing to compromise multiple accounts for multiple systems, they get potentially wide-ranging access with just one successful attack. So the security controls around the SSO system itself and the credentials used for it have to be exceptionally strong.
That single point of failure aspect is worrying. If losing that one authentication server could potentially halt the entire business, how do organizations mitigate that? Are we talking about just standard high availability like clustering, or is there more to it, especially considering geographic redundancy? What's the standard practice?
That's a really critical operational question. You absolutely cannot deploy an enterprise SSO system without robust high availability and disaster recovery built in. At a minimum, the core authentication servers need to be clustered for load balancing and immediate failover within a data center. But best practice, especially for critical services, demands full geo-redundancy. That means having synchronized, mirrored SSO infrastructure running in geographically separate locations. If one entire data center goes offline, the other can take over authentication services. Furthermore, you need well-rehearsed recovery protocols. What happens if the entire SSO Federation fabric fails, perhaps due to a widespread network issue or a catastrophic attack? There must be documented, tested, break-glass procedures that allow essential personnel, particularly the security and infrastructure teams, to gain emergency access using offline or alternative authentication methods to start the recovery process. You're right to be concerned. You are fundamentally concentrating risk. So the resilience and recovery planning around that single point of failure must be absolutely top-notch.
Okay, that makes sense. You have to plan for the worst. Now, what if we need to extend this SSO convenience not just within one organization, but across different independent organizations? That's where federated identity management comes in, right? This is 4.7.1. Let's use that analogy you mentioned, maybe a group of research universities that all need to grant their researchers access to shared data sets hosted by one another.
Exactly. Federated Identity Management, or FEFM, is essentially SSO scaled up to work across organizational boundaries. It allows a user authenticated by their home organization, say University A, to access resources hosted by a partner organization, say University B, without needing a separate account at University B. It requires a high degree of trust between the participating organizations and relies on shared standards and agreements. There are two main models for establishing this trust.
Okay, what's the first model?
The first is called the Web of Trust model. In this setup, every organization in the Federation explicitly reviews and approves every other member organization they want to trust. The advantage here is very high assurance. Trust relationships are direct, peer-to-peer, and usually heavily vetted based on bilateral agreements. The downside, it just doesn't scale well. Imagine 100 universities, each one would potentially need to establish and maintain 99 separate trust relationships.
Great. Sounds like a nightmare to manage. So what's the more common approach, especially in the cloud?
That's the third-party identifier model. Here, instead of managing trust peer-to-peer, all the organizations agree to trust a single, central, external entity to handle the vetting, approval, and maintenance of the trust fabric. This could be a dedicated identity provider service, or often it's a function provided by a cloud access security broker, or CASB. This model scales much, much better because each organization only needs to establish one trust relationship with the central third party. Within any federation, we have specific roles. The organization that authenticates the user, their home organization, is called the identity provider, or IDP. The organizations that host the resources the user wants to access are called relying parties, or RPs. The RPs trust the authentication performed by the IDP.
And to make this all work technically across different systems and organizations, we need standardized communication protocols. This is 4.7.2. You mentioned SAMSTEP 2.0 as kind of the dominant standard here.
Yes. SAML, which stands for Security Assertion Markup Language version 2.0, is definitely the most widely adopted standard for web-based federation. It's an XML-based framework. When a user tries to access a resource at a relying party, the RP redirects them to their home identity provider to authenticate. Once the IDP successfully authenticates the user, it generates a digitally signed XML document called a SAML assertion. This assertion contains information about the user's identity, authentication status, and potentially other attributes, like group memberships. The user's browser then posts this assertion back to the relying party. The RP verifies the digital signature on the assertion to ensure it came from the trusted IDP and hasn't been tampered with, checks its validity period, and then uses the information within it to grant the user access all without the user needing a local account or password at the RP. It enables seamless cross-domain access.
Okay, SAML is the big one, but the guide mentions a few others we should probably just briefly touch on.
Absolutely. There's WS Federation, which is a competing standard primarily developed by Microsoft. It serves a similar purpose to SAML but uses slightly different mechanisms and terminology like the concept of realms to define trust boundaries. Then you have OAuth, usually OAuth 2.0 now. OAuth is specifically focused on authorization, not authentication. It's the protocol that allows you, for example, to grant a third-party mobile app limited access to your data stored in another service, like letting a photo printing app access your Google Photos, without giving the app your actual Google password. It works with access tokens. And finally, there's OpenID Connect. This is a newer standard built on top of the OAuth 2.0 framework. While OAuth is about authorization, OpenID Connect adds a crucial identity layer on top, focusing specifically on authentication, verifying the end user's identity in an interoperable way. It's gaining a lot of traction, especially for consumer-facing applications.
Got it. SAML for Enterprise Federation, Oath for Authorization Delegation, OpenID Connect for modern authentication built on OAuth. Okay, last crucial piece of IAM, the single most effective control we have against credential theft multi-factor authentication, or MFA. That's 4.74. The core requirement is simple, right? Use at least 2 different types of authentication factors.
Simple concept, incredibly powerful in practice. The idea is to layer different types of proof of identity, making it much harder for an attacker who might compromise one factor to gain access. There are 3 main categories, or factors, of authentication. First, something you know. This is the most common factor, typically a password, a PIN, or maybe the answer to a secret question. Second, something you have. This is a physical object in your possession. Examples include a hardware token or key fob that generates a one-time code, a smart card, or increasingly receiving a temporary passcode via SMS or an authenticator app on your registered smartphone. And third, something you are. This refers to inherent biometric traits. Things like your fingerprint, a retina or iris scan, voice recognition, facial geometry, or even potentially DNA signatures, though those are less common in everyday use. Requiring at least two of these different types, like a password, plus a code from your phone, makes a successful attack significantly more difficult. An attacker would need to steal your password and also steal your physical phone or bypass its security. That's why MFA is considered absolutely essential for securing remote access, privileged accounts, and sensitive cloud resources.
Makes perfect sense. Layered defense. Okay, let's shift gears now to some of the supplemental security components and architectural choices that protect the application itself. This is domain 4.6, starting with firewalls, specifically the web application firewall, or WAF. Firewalls have come a long way, haven't they?
Oh, absolutely. Early firewalls were pretty basic, just blocking or allowing traffic based on IP addresses and port numbers. Then came stateful inspection firewalls, which could track the state of network connections, offering better security. But the modern web application firewall, or WAF, operates way up at OSI layer 7, the application layer, and that's the key differentiator. A WAF understands the application's language protocols like HTTP and HTTPS, not just the underlying network packets.
So how does that layer 7 understanding help it catch attacks that a traditional network firewall might miss?
Because it knows how the web application is supposed to behave. Let's say an attacker tries to perform a SQL injection attack by embedding malicious SQL code within a standard web form submission. A traditional network firewall just sees legitimate web traffic coming in on port 80 or 443. It looks fine from a network perspective. But the WAF inspects the actual content of that HTTP request. It understands that a specific input field should only contain, say, numbers, but the incoming request contains characters like semicolons, hyphens, or SQL keywords, select, union, drop. The WAF recognizes this as a potential attack pattern, even though the network connection itself is valid. It can then block that specific malicious request before it ever reaches the web server or the database. WAFs are crucial for stopping common web attacks like SQL injection, cross-site scripting, XSS, directory traversal, and they can also help mitigate things like network-based denial of service or buffer overflow attempts aimed at the web server. In fact, compliance standards like the Payment Card Industry Data Security Standard, PCI DSS, often explicitly require the use of a WAF to protect web applications handling cardholder data.
Okay, so WAF protects the front door of the web application, but what if an attacker gets past that, maybe through a different vector, and starts messing with the data directly inside the database?
That's where you need database activity monitoring, or DAM. A DAM system, which can be a dedicated hardware appliance or software, specifically watches the traffic going to and from the database, or monitors activity directly on the database server itself. It looks for suspicious or anomalous activity, things like a user suddenly trying to access tables they don't normally touch, attempting to escalate their privileges within the database, querying for an unusually large number of records, potential data exfiltration, or executing unexpected administrative commands. It logs and analyzes the actual database queries and operations. DAM solutions typically come in two flavors. You can have agent-based DAM, where you install software agents directly onto the database servers. This gives you very deep visibility into local activity, but the agent itself consumes server resources and could potentially impact performance. Or you can have network-based DAM, which usually involves a physical or virtual appliance that sits on the network segment in front of the database servers and passively monitors the SQL traffic flowing across the wire. This is less intrusive on the database servers themselves, but it might miss encrypted traffic or activity initiated directly on the server console, local admin actions. Often a combination is used.
Okay, WAF for the web front end, GAM for the database backend. Now, we talked about APIs being critical gateways earlier. It makes sense that we have specific security controls for them too, like API gateways.
Yes, gateways are essential control points, especially in modern microservices architectures where you might have dozens or hundreds of internal and external APIs. An API gateway sits in front of your backend API services and acts as a single entry point, a reverse proxy. This offers several security benefits. It hides the complexity and topology of your backend services. More importantly, it's the place where you enforce crucial security policies. You can implement robust authentication and authorization checks, apply rate limiting and throttling to prevent denial of service attacks or abuse, enforce API usage quotas, gather detailed metrics and logs on API calls, and perform security filtering on the requests and responses. Similar in concept, you might also encounter XML gateways. These are specialized gateways focused on securing web services that rely heavily on XML, like those using the SOAP protocol we discussed. They can perform functions like XML schema validation, cryptographic operations on XML messages, and often include data loss prevention DLP capabilities to inspect XML payloads and prevent sensitive data from being exposed inappropriately through APIs.
Right.
Yeah.
Controlling the flow. Let's spend a bit more time on the API architectures themselves now, 4.5.1 and 4.6. We keep mentioning the two main types, RESTful and SOAP. Can you break down the key differences and when you choose one over the other?
Sure. Let's start with RESTful, which stands for Representational State Transfer. This is really the dominant architectural style for web APIs today, especially for public-facing ones and mobile apps. REST is considered lightweight and highly scalable. It typically uses standard HTTP methods, get, post, put, delete, acting on resources identified by simple uniform resource locators, URLs or URAs. It's language independent and generally uses smaller message formats, often JSON, JavaScript object notation, though it can support others like XML, CSV, or plain text. REST APIs tend to be stateless, meaning the server doesn't need to maintain client session information between requests. This makes them easier to scale horizontally. REST works extremely well when bandwidth is a concern, when you need loose coupling between client and server for operations that are inherently stateless, and when you want to leverage HTTP caching mechanisms effectively. It's really built for the scale and nature of the web.
Okay, so REST is lightweight, scalable, uses standard web protocols, often JSON. What about SOAP? Simple Object Access Protocol.
SOP is the older, more formal, standards-based protocol. It's heavily reliant on XML for its message format, defining strict structures using related standards like WSDL, Web Services Description Language, for describing the service, and XSD, XML schema definition, for defining the data types. SOP is generally considered more heavyweight and complex than REST. It's less tolerant of errors. The XML messages have to conform precisely to the defined contract. It's often slower due to the verbosity of XML and the processing overhead. However, SOP has some advantages in certain scenarios. Because it's highly standardized, it has built-in support for things like reliability, guaranteed message delivery, and transactionality, often through extensions known as the WS standards, like WS Security, WS Reliable Messaging. So SOP might be a better choice for enterprise applications requiring high reliability, complex asynchronous processing, strong typing, and formal contracts between systems, or stateful operations where maintaining transaction integrity across multiple steps is critical. While REST often prioritizes performance and simplicity, SOP prioritizes robustness, features defined by formal standards.
So, different tools for different jobs. But regardless of whether it's REST or SOAP, the fundamental security concern remains. The moment you expose or consume an API, you're granting another application programmatic access to your functions and data. This brings us back to the idea of API supply chain management 4.5.2 needing to be really rigorous.
Yes, this is a huge and growing area of risk, especially with the rise of microservices and the heavy reliance on third-party services. What often happens is developers build an application that consumes APIs from several different external vendors, maybe one for payment processing, another for mapping services, a third for identity verification. Then they add their own custom APIs on top of or alongside these. You end up with this complex chain of API calls. The end consumer of the final application, and often even the organization that built it, has very little visibility or control over the security practices of all the upstream third-party API providers in that chain. A vulnerability in any one link can potentially compromise the entire chain. Mitigation here is tough. It requires diligent auditing of contracts and SLAs with API providers, demanding security documentation and certifications, performing regular security assessments or penetration tests on critical third-party APIs you rely on, and having strong internal policies governing which external APIs are authorized for use. It's a complex ecosystem to secure.
Definitely sounds like a major challenge. Okay, let's talk about our last line of defense within the architecture, cryptography. 4.6.2. We absolutely need it for protecting data, both when it's sitting still at rest and when it's moving in transit.
Absolutely fundamental. Protecting data at rest is non-negotiable, especially in a multi-tenant cloud environment. Think about that multi-tenancy issue again. Let's say law enforcement executes a warrant and physically seizes the server hardware that hosts your data because they are investigating another tenant on that same hardware. If your data is not encrypted at rest, it's potentially exposed during that seizure, even though you did nothing wrong. Proper encryption at rest, whether it's whole disk or whole instance encryption, volume level encryption, or even file folder specific encryption, ensures that even if someone gets physical access to the storage media, the data itself remains confidential gibberish without the keys.
And that brings up the absolutely critical point about encryption, key management. Who holds the keys?
The customer must retain ultimate control over the encryption keys. Cloud providers offer various key management services, KMS, which can be very convenient for generating, storing, and rotating keys. But the operational and legal control over who can use those keys and under what circumstances must remain with you, the customer. If the cloud provider holds the keys and has the ability to use them to decrypt your data at will, then the encryption provides very little real security against compelled disclosure or provider access. Best practice often involves using customer-managed keys, perhaps stored in a dedicated hardware security module, HSM, that is either managed directly by the customer or by the provider strictly on the customer's behalf, with strong contractual controls. Key sovereignty is paramount.
Okay, control the keys for data at rest. What about data in transit?
For data moving across networks, especially untrusted networks like the public internet, we need encryption to prevent eavesdropping and man-in-the-middle MITM attacks. The modern standard protocol for securing web communications, like HTTPS, is Transport Layer Security, or TLS. It provides confidentiality, encryption, and integrity, protection against tampering, for data exchange between a client, like your browser, and a server. You'll also still hear about its predecessor, Secure Sockets Layer, or SSL. SSL is technically deprecated. Version 3.0 was officially disallowed back in 2015 due to known vulnerabilities. However, you'll still encounter systems using SSL, or the term being used loosely to refer to TLS, simply because migrating thousands of legacy systems off older protocols is a slow and expensive process for many large organizations. But for new deployments, TLS, currently version 1.2 or 1.3, is the standard you should be using and looking for.
Right, use TLS for transit. Okay, finally, let's cover isolation techniques, 4.6.3, 4.6.4. These are really important for safely testing code or analyzing potentially malicious software. Let's start with sandboxing.
Sandboxing is all about creating a tightly controlled, contained environment where you can run untrusted or potentially dangerous code without letting it affect the rest of your system or network. There are basically two main approaches. A physical sandbox is the ultimate isolation. Think of it like a dedicated lab computer, completely disconnected from the main network, sometimes called air-gapped. It's a separate testbed, isolated hardware, no shared connections. Ideal for analyzing malware, for example. More commonly in development and testing, you use a logical sandbox. This creates an isolated process or restricted memory space within the same operating system, or even within another application, like a web browser running untrusted JavaScript. The sandbox enforces strict rules on what the code running inside it can do, what files it can access, what network connections it can make, what system resources it can use. This allows the developer to safely test a piece of new or untrusted code, or a security analyst to execute malware for analysis, preventing it from breaking out and harming the host system or accessing sensitive data.
Okay, so sandboxing contains untrusted code. How does application virtualization differ? It sounds similar.
It's related but distinct. Application virtualization isn't usually about running untrusted code. It's about running a full, legitimate application in a virtualized environment that abstracts it from the underlying host operating system. Think about needing to run an old critical legacy Windows application on a modern Linux server because the original hardware died. Or maybe you need to test multiple versions of the same application concurrently without them interfering with each other. Application virtualization packages the application along with just enough of its dependencies, like specific registry settings or DLLs, so it can run inside a managed virtual environment, like using Wine on Linux to run Windows apps or tools like VMware ThinApp or Microsoft App V. It allows you to run potentially incompatible or conflicting applications safely on a single host OS, or to deploy applications without needing to fully install them on the endpoint. It provides isolation for compatibility and deployment rather than primarily for containing malicious code like a sandbox does.
Okay, that clarifies the difference. Containing bad code versus running legitimate apps in isolation. Right, we've covered building and architecting the application. Now we need to talk about cloud application assurance and validation, making sure it's actually secure. This is domain 4.4. A key part of this starts way back in the design phase with threat modeling. And a very common model used for this is the Microsoft-developed STRIDE model, mentioned in 4.3.4.
Yes, STRIDE is a really useful mnemonic for developers and architects to systematically think about potential threats early in the design process. The idea is to analyze your application design against each category of threat defined by the acronym. By identifying potential threats proactively, you can then ensure appropriate security controls are designed in from the beginning to mitigate them.
Okay, let's write down the STRIDE acronym itself. What does each letter stand for? And maybe give a quick example of how you think about it during design.
Sure. S stands for spoofing. Can an attacker illegitimately take on the identity of another user, process, or system? When designing a login mechanism, spoofing is a primary threat you'd consider. How do we prevent someone from pretending to be a legitimate user? This leads to controls like strong passwords, MFA, and secure session management. T is for tampering. Can an attacker modify data without authorization, affecting its integrity? Think about data stored in a database or configuration files. How do we prevent unauthorized changes? This points to controls like access control lists, data validation, digital signatures, or checksums. R is for repudiation. Can a user perform an action and later falsely deny that they did it? If your application handles financial transactions, you need strong non-repudiation. This requires controls like secure, detailed audit logging, and potentially digital signatures on transactions. I is for information disclosure. Can an attacker gain access to sensitive information they shouldn't see? This could be data exposure, like revealing PII, or even just revealing details about how the application functions internally that could aid further attacks. Controls here include encryption, proper access controls, and avoiding verbose error messages. D is for denial of service, DOS. Can an attacker prevent legitimate users from accessing the application or service, maybe by overwhelming it with traffic or crashing it? When designing network interfaces or resource allocation, you need to consider DOS threats and implement controls like rate limiting, input validation, and resilient architecture. And finally, E is for elevation of privilege. Can a user with limited permissions somehow gain high-level privileges they aren't entitled to? This is a critical one. You need robust authorization checks throughout the application to ensure users can only perform actions allowed by their assigned role. So by systematically going through STRIDE for each component of your application during the design phase, you force yourself to think like an attacker and build in the necessary defenses up front.
That's a great framework, thinking like the attacker. That helps us anticipate the common ways they try to break in, especially the vulnerabilities that consistently show up on lists like the OSP Top 10. What are some of those perennial weaknesses we absolutely must guard against in cloud application security?
Unfortunately, many of the same vulnerabilities plague applications year after year. Injection attacks remain a huge problem. SQL injection, LD API injection, OS command injection, anywhere user-supplied input is used to construct commands or queries without proper sanitization. Broken authentication is another big one. This covers everything from weak password policies and insecure password storage to session hijacking flaws, like predictable session IDs or sessions that don't expire properly. Cross-site scripting, XSS, is also constantly near the top. This is where an attacker manages to inject malicious scripts, usually JavaScript, into a web page viewed by other users, allowing the attacker to steal session cookies, redirect users, or deface websites. It stems from the application not properly validating or encoding user-supplied data before displaying it. We also see things like insecure direct object references, where an application exposes internal implementation details like database keys or file names in URLs, allowing attackers to manipulate them to access unauthorized data. And sadly, the simple but devastating security misconfigurations, things like leaving default passwords unchanged, enabling unnecessary services, or overly verbose error messages that leak information, these are often just human errors during setup or maintenance. Others include sensitive data exposure, failing to encrypt sensitive PII or financial data both at rest and in transit, missing function-level access control, where the UI might hide a button for an admin function, but the backend doesn't actually check if the user is an admin before executing the function, cross-site request forgery, CSRF, tricking a logged-in user's browser into making an unwanted request to a site they're authenticated to, and critically, using components with known vulnerabilities.
That last one seems huge, especially with the reliance on third-party libraries and open-source components we discussed earlier.
It's massive. Developers pull in libraries to add functionality quickly, but if they don't track whether those libraries have known published vulnerabilities, CVEs, they're essentially importing risk directly into their application. And finally, things like invalidated redirects and forwards can be exploited to send users to malicious sites. It's a long list, unfortunately.
It really is. Okay, before we jump into the specifics of testing for these vulnerabilities, we have to acknowledge that inherent tension again. The quality of service, QoS trade-off. Implementing strong security controls almost always has some impact on performance or usability, doesn't it?
It's an unavoidable reality, and as we touched on earlier, in the cloud, this trade-off often has a direct, measurable financial cost. Take database encryption, for example. Enabling strong encryption for data at rest requires the database server's CPU to constantly perform encryption and decryption operations for every read and write. That consumes significant CPU cycles. It slows down database performance. And in a cloud environment where you pay for CPU usage, RAM consumption, and potentially I/O operations, that performance hit translates directly into higher monthly bills. Similarly, if you deploy host-based intrusion detection systems, HITIDHE, on your servers, those agents need to inspect network traffic, monitor system calls, and analyze logs in real time. This constant monitoring activity consumes CPU and memory resources on the server, potentially impacting the performance of the primary application running there, adding latency, and again increasing your operational costs. Perfect security often means slower performance and higher expenses. Finding the right balance is key.
A constant balancing act. Okay, so knowing these trade-offs, we need effective testing methods to find vulnerabilities without completely crippling the application. Let's clearly distinguish between two major testing approaches mentioned in 4.4.2, vulnerability scanning versus penetration testing.
Right, they sound similar, but they're quite different in practice. Vulnerability scanning is generally an automated, passive process. You use specialized tools like Nessus, OpenVAS, Qualys that contain large databases of known vulnerabilities, configuration errors, and missing patches. The scanner probes the target system or application, compares what it finds against its database of known issues, and generates a report listing potential vulnerabilities. It's great for finding the low-hanging fruit, the known flaws, but importantly, it cannot find new, previously unknown vulnerabilities, the so-called zero-day exploits, because they aren't in its definition database yet.
Okay, so scanning is automated, looks for known flaws, and is passive. What about penetration testing?
Penetration testing, or pen testing, is a much more active and often manual process. The goal isn't just to find vulnerabilities, but to actively attempt to exploit them to gain unauthorized access, escalate privileges, or achieve a specific objective, like extracting sensitive data. Pen testers use a combination of automated tools and manual techniques, mimicking the actions of a real attacker. They try to chain vulnerabilities together, bypass security controls, and demonstrate the actual impact of a flaw. Because it involves actively attacking systems, penetration testing always requires explicit written authorization from the system owner beforehand, along with clearly defined rules of engagement specifying scope, timing, and limitations. You can't just start pen testing someone's systems without permission.
Right, permission is crucial for pen testing. Now, within the realm of application security testing itself, there are two fundamental methodologies for analyzing the code and runtime behavior. SAST and DAST. Let's break those down.
Okay. First, we have SAST, which stands for Static Application Security Testing. This is often called white box testing. Static means we analyze the application source code, or sometimes the compiled bytecode, without actually running the application. White box means we have full visibility into the internal workings of the code itself. SAST tools scan the source code, looking for patterns that indicate potential security vulnerabilities based on known insecure coding practices or specific flaw signatures. It requires access to the source code, and the analysis is typically done by specialized security analysts or developers who understand both secure coding principles and the language the application is written in. Ideally, the person doing the SAST review should not be the same person who wrote the code to provide an independent perspective.
Okay, so SAST looks directly at the code without running it. What kinds of vulnerabilities is it particularly good at finding?
SAST excels at finding certain types of flaws that are visible directly in the code logic itself. Things like potential null pointer to references that could crash the application, the use of insecure or outdated cryptographic functions, like using MD5 for hatching passwords instead of a modern algorithm like bcrypt, logic errors and access control checks, potential race conditions, hard-coded passwords or API keys directly in the source code. Surprisingly common mistake. SAST gives you a high degree of confidence about the internal quality and security posture of your code base itself. But its limitation is that it doesn't know anything about the actual environment where the code will run, the server configuration, the network setup, interactions with other systems.
Which leads us perfectly to the other side of the coin, DAST, or Dynamic Application Security Testing.
Exactly. If SAST is static, DAST is dynamic. If SAST is white box, DAST is typically black box testing. Dynamic means we test the application while it is running. Black box means the tester interacts with the application from the outside like a real user or attacker would without having access to the internal source code. They provide inputs through web forms, API calls, etc., and observe the outputs and behavior of the running application to identify vulnerabilities.
So if DAST doesn't see the source code, what kinds of vulnerabilities does it find that SAST might miss?
DAST is excellent at finding issues that only manifest themselves when the application is actually executing in its intended environment. This includes runtime environment configuration issues like server misconfigurations, incorrect HTTP headers, authentication or session management flaws that arise from how the server handles sessions, patch-level issues in the underlying OS, web server, or application framework that SAST wouldn't see, and certain types of injection flaws or cross-site scripting that might depend on how live application processes specific data inputs, which might be hard to spot just by looking at the static code.
It sounds like you really need both SAST and DAST for comprehensive application security testing then. They find different kinds of things.
Precisely. They are highly complementary, not mutually exclusive. A robust application security program absolutely needs to incorporate both static analysis of the code and dynamic testing of the running application. Some vulnerabilities, like certain types of SQL injection or XSS, might actually be detectable by both methods, which just reinforces their importance. Using both SAST and DAST together gives you much greater assurance. SAST helps ensure the internal code quality is high, while DAST helps ensure the application is secure when operating in its actual production or staging environment.
Okay, SAST for code quality, DAST for runtime security. Got it. Now let's move into our final section, focusing on ensuring we're using verified secure software and maintaining a secure network environment. This touches on domains 4.5 and 5.2. We've already stressed the risk of using components with known vulnerabilities. This naturally leads to the ongoing debate. Open source versus proprietary software, what are the trade-offs from a security perspective?
It's a complex debate with valid points on both sides. Open source software offers potential benefits, like transparency in theory. Anyone can audit the source code for vulnerabilities. It offers flexibility and avoids vendor lock-in, and of course it usually has a lower direct acquisition cost, though total cost of ownership can vary. Proprietary software, on the other hand, comes with vendor accountability. You have a contract, SLAs, and someone presumably liable if their software has a major flaw, though liability is often limited. You typically get structured support, regular patches, and guaranteed active updates as part of the license fee. From a security standpoint, neither is inherently more secure. Open source relies on community vigilance and transparency, while proprietary relies on the vendor's internal processes and reputation. The real risk often comes down to how well either type of software is managed and maintained within your organization.
And that management often ties back to the development methodology used, right? You mentioned the agile development risk earlier in the context of potentially pulling in insecure components.
Yes, it's a significant factor. Agile methodologies prioritize rapid iteration and timely delivery of functional software. To meet tight deadlines, developers under pressure might be tempted to grab a readily available open-source library that solves an immediate problem without fully investigating its security track record, its dependencies, or its long-term maintenance prospects. This focus on expediency can lead directly to that problem of using components with known vulnerabilities. If the serious security flaw is later discovered in that quickly integrated open source component, and maybe the original project is no longer actively maintained, well, you might be stuck. There might be no easy patch available, forcing a potentially very costly and time-consuming effort to rip out the vulnerable library and re-architect that part of the application. It's a classic example of technical debt incurred for the sake of short-term speed.
A real danger. Okay. Shifting slightly, when you have complex business processes that require multiple different applications to interact and coordinate their actions, the guide mentions that application orchestration, 4.6.4, is generally preferred over just directly linking the applications together. Why is that abstraction beneficial?
Direct linking, where application A makes direct calls to application B, which then calls application C, creates very tight, brittle dependencies between the applications. If application B changes its interface or internal logic, application A might break unexpectedly. Version control becomes a nightmare. Orchestration introduces a middle layer, an orchestrator engine or service. This orchestrator manages the overall workflow, coordinating the sequence of calls between the different applications, handling data transformations if needed, and managing error conditions. By abstracting the control flow away from the individual applications, orchestration promotes looser coupling. Applications become more independent and reusable. It simplifies managing changes and updates because you modify the orchestration logic rather than potentially recoding multiple applications. While it adds its own layer of complexity, it generally leads to a more resilient and manageable system when multiple applications need to collaborate on a complex task. It might require defining standardized interfaces or protocols for the orchestrator to talk to each application.
Okay. Orchestration for managing complex interactions. Finally, let's anchor all this application-level security discussion by briefly touching on the necessary foundation, the secure network environment itself. This pulls from Domain 5, specifically 5.2, in the context of supporting applications.
Absolutely. Secure applications rely on a secure network underneath. There are a few core networking concepts mentioned that are essential. First, VLANs, or Virtual Local Area Networks. VLANs allow you to logically segment a physical network into multiple broadcast domains. Devices on one VLAN can't directly talk to devices on another VLAN unless the traffic passes through a Layer 3 device, like a router or a firewall, that controls the flow between them. This segmentation is crucial for isolating different types of traffic, ZD, separating user workstations from sensitive servers, and limiting the blast radius if one segment is compromised. Second, we have DNS and its security extension, DNS-SEC. DNS, the domain name service, is what translates human-friendly domain names, like www.example.com, into the IP addresses computers use to communicate. It's fundamental to how the internet works. However, standard DNS is vulnerable to attacks like cache poisoning or spoofing, where an attacker can trick users into connecting to malicious servers by providing fake DNS responses. DNS-SEC, DNS security extensions, adds a layer of security by using digital signatures to provide origin authority, proving the response came from the legitimate DNS server, and data integrity, proving the response wasn't tampered with. Implementing DNS-SEC helps mitigate these serious DNS hijacking threats. And third, the VPN, or Virtual Private Network. A VPN creates a secure, encrypted tunnel over an untrusted network, most commonly the public internet. VPNs are fundamental for providing secure remote access for employees working from home or on the road, allowing them to connect back to the corporate network as if they were physically there. They're also commonly used to establish secure, persistent connections between an organization's on-premises network and their virtual private cloud (VPC) environment in the cloud, ensuring the confidentiality and integrity of the data flowing between those two environments.
VLANs for segmentation, DNS-SEC for trustworthy name resolution, VPNs for secure tunnels. Got it. Core networking hygiene. All right, that was an incredibly detailed journey through Domain 4, Cloud Application Security. We covered a massive amount of ground, from readiness in the SDLC to IMM, architecture, testing, and the network environment. Let's try to quickly recap the absolute must-know concepts for anyone studying for the CCSP exam.
Okay, rapid-fire recap. Architecturally, remember the WAF Web Application Firewall. It operates at OSI Layer 7, understands HTTP, and protects against web-specific attacks like SQL injection and XSS. Know the difference between the main API architectures. REST is lightweight, scalable, uses HTTP verbs, often JSON, great for web mobile, usually stateless. SOAP is more formal, XML-based, standards-driven, better for complex transactions, stateful operations, and guaranteed delivery.
For the secure SDLC, that distinction between the frameworks is key. ONF, Organizational Normative Framework, is the big organization-wide master list of all approved security controls and practices. ANF, Application Normative Framework, is a specific subset of controls from the ONF that apply to one particular application based on its risk. Remember, ONF to ANF is one-to-many. ANF to ONF must be one-to-one.
Testing methodologies are critical. Know the difference. SAST, Static Application Security Testing, is white box, analyzes the source code itself without running it, finds internal coding flaws. DAST, Dynamic Application Security Testing, is black box, tests the application while it's running, finds runtime configuration and environmental issues. You absolutely need both for good coverage.
For identifying threats early, remember the STRIDE model: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. Using STRIDE during the design phase helps you build security in from the start.
And don't forget that crucial legal point about shared responsibility. Ultimate legal responsibility for securing the data always remains with the customer, the data owner, regardless of what your contract with the cloud provider says about financial liability for breaches caused by their negligence. That liability to regulators and affected individuals is yours.
Fantastic summary. Building secure applications in the cloud clearly requires more than just good coding. It demands a really systematic approach, weaving together identity management, secure architecture, rigorous testing, and continuous validation throughout the entire lifecycle. Ultimately, it's how organizations can deliver powerful business functions while still maintaining the trust of their users and customers.
Absolutely well said. And maybe if I can leave our listeners with one final thought to chew on, something to explore further. We talked a lot about the speed benefits of the cloud and agile development. But that speed often directly contributes to what I think is arguably the single most common security failure in modern applications: knowingly or unknowingly using components with known vulnerabilities. So the provocative thought is, how can your security team effectively integrate automated security scanning tools, specifically things like software composition analysis, SEA tools, which identify open source components and their known vulnerabilities directly into the automated build and deployment pipelines, the CI/CD process. The goal should be to automatically flag and ideally block deployments that contain components with known critical flaws before they ever get pushed to production. Making security part of the automated workflow, not just an afterthought review, seems like the next frontier.
That's a great challenge and a perfect place to wrap up. How do we automate finding those known vulnerable components before they bite us? Excellent food for thought. Thank you so much for guiding us through that incredibly detailed domain. And thank you, our listeners, for joining us on this deep dive into cloud application security. We hope you found it valuable for your CCSP journey, and we look forward to having you back as we continue exploring the next domain.